What if the key to solving quantum computing's biggest roadblock, its incredible fragility, wasn't about better engineering at all? What if it was hiding in a secret mathematical pattern that connects everything from Fibonacci numbers to the mysteries of antimatter? Well, today, we are diving into a really radical proposal that claims it's found just that, a blueprint for a quantum computer that is, get this, born fault-tolerant.
All right, so here's our game plan. First, we're going to look at the huge wall that quantum computing is currently running up against. Then we'll dig into the mathematical blueprint that some say could just smash right through it. We'll see how this hourglass shape could lead to a totally new kind of machine. We'll check out its pretty wild performance claims, and then we'll see how it could even revolutionize computer memory, and finally we'll look at the roadmap to turn all of this from theory into reality.
So first things first, we really have to understand the scale of the challenge. Right now, we're in what people call the noisy intermediate scale quantum era, or NISQ for short. And that era is defined by one massive fundamental barrier that has, so far, completely stopped us from building the truly powerful, large-scale quantum machines we've been dreaming of.
And that really is the million-dollar question, isn't it? As we try to build these things bigger with more and more processing power, they don't just get more powerful, they also get exponentially more unstable. It's this super frustrating paradox that has basically defined the entire field for years.
This enemy, it has a name: decoherence. You see, a qubit's quantum state is unbelievably delicate. The tiniest vibration, a slight change in temperature, even a stray magnetic field, any of it can just knock it right out of its quantum state, completely destroying the calculation. It's like trying to build a perfectly stable skyscraper on a foundation that's literally made of shifting sand.
So this creates the core problem of the whole NISQ era. The goal has always seemed so simple, right? Add more qubits, and you get more computational power. But the reality is that every single qubit you add is another potential point of failure, another little antenna for noise. In practice, scaling up has just meant scaling up the error rate. We've hit a wall that just tweaking things a little bit here and there can't seem to break through.
So how in the world do you solve a problem like decoherence? Well, the Perez Hourglass proposal argues that maybe we've been looking in completely the wrong place. Forget better engineering for a second. It points to a complete architectural blueprint discovered not in some physics lab, but deep within the landscape of pure mathematics.
And this sketch from 1997 is where the whole idea started. It begins with something you might remember from math class, the simple additive pattern of Pascal's triangle. But then it does something really interesting. It superimposes a mirrored version that subtracts instead of adds, its mathematical antimatter opposite. When you lay them together, this hourglass shape just emerges. And what's incredible is that hidden right there in its diagonals is the famous Fibonacci sequence.
What's really wild is how this one single hourglass structure seems to act like a kind of mathematical Rosetta Stone. It doesn't just connect Pascal's triangle to things like Fibonacci. The claim is that it unifies all these different mathematical patterns, from fractals to some of the deepest, weirdest mysteries in number theory. The core idea here is that this isn't just some cute coincidence. It's a sign of a deeply fundamental pattern woven into the fabric of nature.
And this gets us to the core philosophy of the whole proposal, which Kepler summed up perfectly centuries ago. The idea is that this deep, unifying mathematical geometry isn't just an abstract curiosity for mathematicians. It can be translated directly into a physical machine that uses these built-in properties for a massive computational advance.
Okay, so you've got this beautiful piece of math, but how on earth do you turn it into an actual machine? Well, the answer lies in this really fascinating concept of balance and, well, annihilation.
So the top half of the architecture is built from that simple additive pattern of Pascal's triangle. In the language of this proposal, this represents the matter side of the whole equation.
And the bottom half is its perfect opposite, a mirrored version of the triangle that uses subtraction instead of addition. This is what's described as digital antimatter, and it creates this perfect fundamental symmetry in the structure.
Now here comes the magic trick. When you map this hourglass geometry onto a physical grid of qubits, the claim is that it becomes inherently self-stabilizing. Think of it like a perfectly designed funnel. Any environmental noise, all those errors, are naturally drained by the shape down towards that narrow waist. And at that central point, the positive matter side meets the negative antimatter side, and the errors are literally canceled out, annihilated. It's a machine that doesn't just resist errors, its very shape is designed to destroy them.
Okay, an elegant theory is one thing, but does it actually work?
Well, the proposal backs all this up with simulation data that points to a pretty revolutionary leap in performance. So let's compare this to one of the leading approaches we use today. The key number to look at here is code distance. Just think of it as a measure of how good the error correction is. To get a really strong code distance of 21, the Hourglass simulation needed just under 1,600 physical qubits. Now, to get that same level of performance with a conventional design, you would need a machine that is way, way larger and more complex. We're talking about a massive claim of efficiency.
This passive error-draining effect is claimed to have a direct, measurable benefit. By encoding a single logical qubit across the two symmetric halves of the hourglass, simulations show a 30% gain in the final state's accuracy, its fidelity, compared to standard methods under the exact same noisy conditions. This is the claim that makes everyone in the field just stop and pay attention. The efficiency is supposedly so profound that it could fast-forward the timeline for breaking the very encryption that protects most of our digital world. The proposal states it could crack a standard 2048-bit RSA key with fewer than 10,000 qubits. That's a number that puts a quantum threat, which many experts thought was decades away, potentially within our reach.
And if you thought that was wild, get this. The claims don't even stop with quantum computing. The creators of the Hourglass believe its unique mathematical properties could also solve a completely different problem, creating a revolutionary new form of classical computer memory.
It's called PAM, which stands for Paz Hourglass Associative Memory. Now, associative memory is a really cool concept that works more like a human brain. You retrieve data based on a piece of the content, not some specific file address. PAM is claimed to be the ultimate version of this, with a theoretical capacity that is basically infinite. Near instant retrieval, and an almost unbelievable resistance to data corruption.
I mean, listen to this bold claim from the source material. It frames FOM not as just an incremental improvement on the memory we have today, but as a complete paradigm shift, a move to a mathematically perfect system.
The simulated numbers here are just staggering. I mean, compared to other models that have hard limits on how much they can store, FAM's capacity is theoretically infinite. Its retrieval speed is in microseconds. That's thousands of times faster than milliseconds. But the most mind-bending claim is its noise tolerance. It can supposedly recover data even if 99% of it has been destroyed. Just think about that for a second.
Okay, so this all sounds absolutely incredible in a computer simulation. But what about the real world? How do you actually go about building one of these things? Well, the proposal lays out a surprisingly concrete roadmap to take this from paper to a physical machine.
And the plan is definitely ambitious. It starts in year one by just testing the core ideas on existing quantum computers that we have today. Then, by 2028, the goal is to build a dedicated demonstrator using a technology called neutral atoms. The final step, which is targeted for 2029, is to design that full-scale 1597 qubit processor, the machine that could theoretically deliver on all these promises with qubits that are stable for over 30 seconds, which would be a massive achievement all by itself.
In the end, the Perez Hourglass proposal is more than just a new design for a computer. It really asks us to imagine a future where the geometry of the machine and the computation it performs are one and the same. A future where the structure isn't just holding the processor, the structure is the processor.